All right, so this video is going to be the first video where we do a cycle. So a cycle is a series of processes that happen one after the other, where by the end of it, you end up where you started in terms of the state of the fluid. The cycle we're going to do today is called the Otto cycle, OTTO. Which is a little confusing because it's actually the cycle that's used in a car engine. So it's a piston cylinder where we have some gas, and that can be, we're going to assume it's air. It's a piston cylinder with some gas. And the first step is the gas gets compressed because the piston moves down and squeezes the air. So the pressure and the temperature both increase because ideal gas law. And then the second step is you're going to add heat to the system. Now, in a real car engine, what happens is this spark plugs fire, and the gasoline that's in the engine then ignites, and that's how you add heat to the system. But we're going to treat it a little differently in this case. We're going to model it as some external input of heat to the cylinder, just like we did looking in the cylinder questions that we've had in earlier chapters. We're going to assume that some external source of heat is adding heat to the cylinder, but that chemically speaking, the contents of the cylinder, even during the combustion process, remain the same. Because for us, again, it's not really a combustion. For us, we're just pretending that heat is being added from the outside. So we compress, we add heat, and then we expand. And the expansion, these high pressure gases push back against the cylinder, they force it downwards, and that then, of course, the gases are at a lower pressure because the volume of the cylinder just increased as you push back on the cylinder. The temperature as well goes down a little. But by the end of the expansion, the state of the fluid is still not the same as where we started. So we have to add a fourth process to bring us back. And that fourth process is the heat rejection process. So in the heat rejection process, it's sort of the antithesis of the heat addition process. So in real life, what happens? Well, the exhaust valve opens up and the exhaust gases leave the cylinder. But in our case, what we're going to do is we're going to say that, like, again, the questions we've done before, we're just having some amount of heat just be rejected from the system. And this is going to bring us back to the state that we need so that we can complete the cycle, and we do it again. Now, why even have such a cycle? Like, what's the point in just like going in circles? Well, it's because each time you do this cycle, you are producing some amount of net work, right? You put in heat, which costs you, right? You even reject some heat, which you lose and you never get back. But the difference between those heat addition and the heat rejected is the work output. And that's what you need to run an engine of a car or a plane or other cycles like that. So let's draw it out a little bit. We have first states. We'll just draw on the bottom left corner. Between the first and the second, sorry, that looks more like a 2 than a 1, excuse me. Between the first and the second state, we have compression. Okay, so we have compression. I'll just write. Okay, so we start state 1, we get compressed, and then we're at state 2. And then we go to state 3, where we have heat addition, which will bring us to state 3. So we'll call this Q in because we're adding heat to the system. Then we go to state 4, where we now expand. This is where we're getting all that work output from. So we call this expansion. And then we have heat rejection, Q out. And the reason, of course, we have this is so that we can eventually go back from 4 to 1 and continue the cycle. So we're going to solve a cycle like this in this video, we're going to solve a cycle, and we're going to look at a couple things. First, we're going to look at the temperature and the pressure at states 1, 2, 3, and 4. And we're going to then look at the thermal efficiency of the system. And we're going to talk a little bit later about what thermal efficiency means. But in order to solve the temperature and pressure, i.e. the state of each, at each state, we need to know a little bit of information about, in this ideal cycle, the types of processes that are happening. So yes, we have compression, we have heat addition, but what remains constant throughout these processes use as a link from one to the other, from one state to the other? And this is something you're going to have to sort of just know and memorize. So in the ideal case, and in this cycle, because everything's the ideal case in this cycle, compression is done, and expansion. Actually, I'll just do compression and expansion. It's done in a type of process called isentropic. Now, it sounds similar to polytropic, which you already know about, right? But it's a little different. It's actually a very specific case of a polytropic process, if you want to look at it that way. And we know from a polytropic process, we always have that exponent we talk about. Sometimes we call it N or K. Well, in an isentropic process, when that exponent is equal to a very specific value, the polytropic process becomes an isentropic process. And that exponent that we're going to use for an isentropic process, we sometimes call it K, sometimes we call it gamma. We'll call it gamma in this case. But it's equal to Cp, which we know, over Cv, the ratio of the specific heat capacities. So for air, and this is something you'll also want to memorize just for convenience, this value is 1.4. Okay? Now, whenever we have sort of a polytropic process with air where N is 1.4, this is what we really call an isentropic process. All right? So mathematically, that's the difference between a polytropic and an isentropic process. A polytropic process could have pretty much any N value, but the isentropic process has a value specifically of Cp over Cv, which for air is 1.4. And we're going to assume air in most of these cycles, including this question. Now, what does an isentropic process mean physically? Well, from the name isen something, we can tell that it's the same, whatever we're talking about, entropic. So the entropy of the system has to be the same. So if we say that the compression and the expansion are isentropic processes, that means that going from 1 to 2, the entropy is the same. And that going from 3 to 4, the entropy is the same. Now, entropy is a property, just like internal energy or enthalpy or specific volume. And you're going to learn a little bit more about it in class and in the next chapter as well. But for now, all you need to know is that it's a property that when it's the same in some process, we're actually able to produce what we call the isentropic relations. And the isentropic relations are a set of relationships between temperature, pressure, and specific volume. And these relations basically allow us to go evaluate certain properties in an isentropic process between the beginning and the end of the process. So I'm going to write out what these relations are. And we're going to keep them always with us whenever we do these types of questions, because they're very important. So first relationship relates the temperature and the volume. So T2 over T1 being the temperature at the end of the process over the temperature at the beginning of the process is equal to the volume 1 over volume 2 to the gamma minus 1. So what is this saying? It's saying that the temperature at the end divided by the temperature at the beginning is equal to the volume at the beginning divided at the volume of the end. In other words, what this tells us is that temperature increases when the volume decreases, which kind of makes sense because we know about ideal gases, PV equals MRT, right? This makes sense, but this is just in the case of an isentropic process, it doesn't just decrease in any way. It decreases specifically V1 over V2 to the power of 1.4 minus 1 if it's air, gamma minus 1 in general. So this is the first of three relations we're going to need to keep in mind. The second relationship is T2 over T1 equals P2 over P1. I'm just going to write that a little clearer because I know the handwriting there wasn't amazing. P2 over P1 to the gamma minus 1 over gamma. The exponent is gamma minus 1 over gamma. So what's this saying? Well, again, it's pretty much saying what we already kind of knew from the ideal gas law, is that if the pressure increases, I'll put it the other way, actually. We'll start with pressure. If the pressure increases, so too does the temperature. We kind of already know this, but now we're saying in the case of an isentropic process, so a compression or an expansion process in the Otto cycle, it's going to increase exactly according to this relationship over here. And the last one we're going to do, the last isentropic relation, is this. P, this is supposed to be pressure, not rho. P2 over P1 equals over specific volume 2 to the power of gamma. Again, to us, this makes sense from the ideal gas law, right? So as specific volume goes up, pressure goes down. In other words, as the density decreases, the pressure decreases. Sorry, as the density, decreases, so too does the pressure. So this is really what something we already knew, but it's again just saying in the case of an isentropic process, it increases exactly according to this relationship. So of course, V goes up, P goes down. Or in other words, density goes down, pressure goes down, right? Because V is just 1 over P, and 1 over rho, excuse me. So these three relations are known as the isentropic relations. So they're extremely important in these types of questions. Why? Because 2 of the 4 processes we do here in this type of cycle, an Otto cycle, are isentropic. So if we want to start looking from 1 to 2, or from 3 to 4, or even backwards, it works the same way, from 4 to 3 and 2 to 1, you're going to use these relations. So if I ask you to find the temperature at state 2, and you happen to know the temperature at state 1 and the change in pressure, well, then you know the temperature at state 2. You don't need to use any property tables or anything beyond these relations here in those cases. Okay, so we've now covered processes like compression and expansion in the Otto cycle, but what about the heat addition and heat rejection processes in this Otto cycle? So are these isentropic? Well, you'll find out in class what an isentropic process really means, and one of the restrictions is that an isentropic process cannot have any heat exchange. So immediately we can say that the process of heat addition, heat rejection are definitely not isentropic. But let's think about what's actually happening in a car engine and see if that sheds any light on us. Actually, I'll draw it the other way. I think it's a little clearer. So we have 4 states, right? So we'll draw 4 different cylinders. So in the first state, in the first state, we have the piston right over here, and the gas is inside the cylinder. We go compress the fluid, so we move the piston cylinder all the way up, and now the fluid is in this much smaller area, and we're at state 2. And then we have this heat addition that kind of happens. And when the spark plugs fire, the piston still has not moved. It's just that now we're adding in heat. And then we expand back down, and this is where you get the work output. You throw the piston from very high up to very low down. That work is what you're getting when you run an engine of any kind. Okay, and of course, to go back from state 4 to state 1 is when we have that heat rejection. But the point is that this heat is added, and same way it's rejected at constant volume, right? The piston is not moving when the heat is being added or rejected. So necessarily the volume is constant. So it's an isochoric process. So the volume is constant, the specific volume is constant. That's the type of process we're dealing with in 2 to 3 and 4 to 1. So how are we going to calculate this in general for Otto cycles? Well, we know from, I think it was chapter 3 or 4, we talked a lot about piston cylinder devices. And in some cases, there was heat being added or rejected. And that's exactly what this is. And we found in that chapter, and I'll draw it over here. We found in that chapter that when we have heat being added or rejected from the system, we have a piston cylinder, we have, let's just say, Q out, for example. We found that the amount of heat rejected was equal to the change in internal energy, right? So let's say we're looking at the heat addition process. So U3 minus U2. Sorry. So that in that case, this would have to be Q in if it's a heat addition, right? Q in, and the arrow is pointing here. So this would be states 2 to 3, for example. So the amount of heat that we transfer is just, in terms of kilojoules per kilogram, it's just U3 minus U2. And we know that we can express this in terms of temperature. Instead of Cp, we're going to use Cv, T3 minus T2 for an ideal gas. So this is how we're going to calculate the amount of the change in temperature caused by the heat addition or the heat rejection. Okay. So if we continue now, let's start looking at actually solving the specific problem that we are given. So this problem is, I'm going to start it on a new page just so it's a bit clearer. So we have a Otto cycle, just as we spoke about, and we're given some information. The V1 being the specific, volume 1 over volume 2, not specific, just volume, is equal to 8. This is what they're telling us about the cycle. That means that when the piston cylinder moves from the lowest point, called bottom dead center, to the highest point as it compresses the fluid, and that's called top dead center, the change in volume of the space that the fluid is able to occupy goes from being 8 times as large to just 1. Okay, so it gives you this parameter, also known as the compression ratio. You'll see a lot in the Otto cycle, and it's really, really important in terms of thermal efficiency, which we're going to talk about later. But what it's telling you is basically how much the piston is squishing the fluid in the compression and expansion process. Because remember, eventually it's going to have to then throw the piston down the same amount and increase the volume by the same factor. So we're told that the compression ratio is 8. At the beginning of the compression stroke, so this is state 1, so just before we start compressing, but just before we start compressing at state 1, we have a pressure of 0.1 megapascals, so 100 kilopascals, so basically atmospheric pressure, and a temperature of 15 degrees Celsius. Okay, so 100 kilopascals, 15 degrees Celsius. This is the international standard atmosphere at sea level. All right, so these values kind of make sense. We can see where they come from. So this is, of course, state 1. They then say that the heat transfer to the air per cycle, So in other words, the heat transfer process, that was process going 2 to 3, is Q in is 1800 kilojoules per kilogram. All right. And this is all the information we're going to get. And they're telling us find the temperature and the pressure at each point and the thermal efficiency. So let's start with the cycle. Let's start with state 1 going to state 2. So if we go from state 1 to state 2, this is a compression process. This is an isentropic compression process. And we also know the V1 over V2 is a value of 8, right? So the first volume is 8 times as large as the second volume, being before and after the compression. So we want to find both the temperature and the pressure. How can we do this? Well, remember we spoke about these isentropic relations. Now we're going to get to see them in action. So, sorry about that. What we're going to do is T2, we're going to use the first relation, which is T2 over T1 equals V1 over V2, which we're given here. It's the compression ratio, right? So V1 over V2 to the power of K minus 1, or well, okay, they use K, we'll use gamma, it doesn't really matter. Point is, it's the CP over CV. Okay, sorry for the dog noises in the background. We had the doorbell ring, so that had to happen, I guess. So T2 equals, if we just rearrange this a little, V1 over V2 to the gamma minus 1. T2 equals T1, we're told, is 15 degrees Celsius, but we can't work with Celsius anymore. We have to put it into Kelvin. So plus 273, T1 becomes 288 Kelvin. V1 over V2, it's the compression ratio, so 8. And we said for air, gamma minus 1 is just 1.4 minus 1. And this should give us the temperature 2, or in other words, the temperature by the end of the compression process. 288 times 8 to the power of 1.4 minus 1 gives us 661.65. So we'll just call it 662 Kelvin. We'll just round. So does this value make sense? We went from 288 to 662. The temperature increased. Is it okay that the temperature increased? Do we expect it to increase, decrease, or what? Well, it's a compression process. So naturally we expect, as we saw from the isentropic relations, and as we kind of already knew from ideal gas law, we expect the temperature to now go up. So that makes sense. We're happy with this value. So we still want to find the pressure, though, at state 2. And good news, we have another relation we can use for that. And let's look at the second isentropic relation, which is T2 over T1 equals P2 over P1 to the power of gamma minus 1 over gamma. So we just found T2. We are given T1. We know P1 from the question. We can isolate for P2 this way. So if I do 662 over 288, and I do all of this to the power of gamma over gamma minus 1, this will equal P2 over P1, which P2 is what we're trying to find. And P1 we're given is 100 kilopascals, right? So we're going to get an answer in kilopascals. So let's do this, 662 over 288 to the power of gamma over gamma minus 1 times 100. And I'm getting a pressure at state 2 of 1.841 megapascals. So 1841 kilopascals. And what I'm going to do is I'm just going to box each temperature and pressure we find. Okay, so what have we done so far? We've just seen how to go from I just want to make sure my mic is on, actually. Yeah. It would be a bad time to now realize that it wasn't on. So we just went from state 1 to state 2. We went from standard atmospheric conditions, which were given in the problem, to 662 Kelvin, and obviously a much higher pressure. This is the purpose of the compression process. We're going to increase the pressure. So now we're ready to go through the next process, which is the heat addition. So the heat addition happens in the combustion chamber. It's the spark plugs firing. But in this case, like we said, we don't want to have to deal with the complexities with combustion. So we're just going to assume that heat is added from an external source, like we've done a million times in chapters 3 and 4. So heat addition, we already said we're doing in an isochoric process. The volume is the same. So that means if we look and if we treat this as an ideal gas, which we can, and I'm just going to start doing it on this side, we know that the volume, or we know specific volume of an ideal gas is RT over P. And if V1 is V2, then that means RT1 over P1 equals RT2 over P2. Now, sorry, we're dealing with states 2 and 3. Excuse me. This should be 2, and this should be 3. So now we're on to the next process. So the R's cancel out. And we can say, and we know T2, we found it before in the first process, we found T2. We also found P2. So what we can do here is we can say that T3 is equal to T2 P3 over P2. The problem is, though, we have too many unknowns here. So what are we going to do? Well, remember, we're given this information here. We're told that there's 1800 kilojoules per kilogram. And we know that for a cylinder device, the amount of heat added to the system is equal to Cp, right? That's correction. That's enthalpy. Is equal to Cv delta T. Cv delta T. All right. Now Cv we can quickly grab from the table for air. We can get Cv for air. T2 is known. All we're doing here is solving for T3. And then if we plug that into the equation here, we can solve for P3. So, and then of course we'll have both temperature 3 and P3, and all we have left to do is solve state 4. So if we get Cv from the table and we plug in T2, which was 662, we'll find temperature 3 of 3174 Kelvin. So if we plug everything in and we solve for T3, and I'll just put a check mark because these are known or knowable, we have 3174 Kelvin. Now this is the temperature after the heat is added. So after the spark plugs have fired, or in our case, after we've added heat from an external source, the temperature of the fluid is now 3174. So if I want to now find the pressure, can I use the isentropic relations? No, because the isentropic relations, as the name would imply, are for isentropic processes. And we know, or you'll learn in class, that an isentropic process cannot have heat addition or rejection. So since we're adding heat, this is exactly what this step is. We can't call this an isentropic process. But we could use the ideal gas law and do sort of what we got over here. So if now in this case, we will actually be solving for P3, not T3, but we know T3, we know T2, we know P2. So if we plug this guy into here, we're going to get P3, which is 8.813 megapascals. So the pressure, the temperature are now super high. This is as high as they're going to get in the entire cycle. And now we're ready to use all that energy stored in this state, and we're ready to expand it to something of a lower energy state. And the difference in energy from state 3 to state 4 is very much the amount of work that we're getting out of the system. So let's go see what state 4 is, and we'll just do that, I guess, here. Now remember, going from state 3 to 4, state 3 to 4 is a is an expansion process, which we saw is an isentropic process. So going from 3 to 4, we can use those relations we were using over here. We can use these again. Now we know state 3. So let's start moving into state 4 and seeing what happens. So before, we had a compression ratio of 8, meaning the volume went from 8 times bigger to 8 times smaller, or went from 8 times as big to something smaller. In this case, though, we're going to expand, and we're going to expand the same amount. So if our volume is 1 cubic meter, we're going to suddenly jump as we throw the cylinder back and produce that useful work. We're going to jump our volume from 1 meter cubed to 8 meters cubed. So we can actually do this very similar to how we went from step 1 to 2. We can go from 3 to 4. But in this case, instead of using 8, V1 over V2 is now 1 over 8, because we're not going from big to small, we're going from small to big. All right, but that's really the only difference. So if we do this T2 over T1, and instead we call it T4 over T3 equals V3 over V4 to the power of gamma minus 1. Again, where 3 and 4 are states 3 and 4. We know T3, we can use this to find T4. So T4 equals T3 to the V, and these should be strike throughs. V3 over V4 to the gamma minus 1. T3 we just found over here. V3 over V4, well, we don't know individually what the volumes are, but we know that V3 is an eighth of V4. So V3 over V4 is 1 over 8. So it's 3174 times 1 over 8 to the gamma minus 1, which we know is 1.4 minus 1. So if we do this, sorry, let me just change here. So if we do this, we'll get that T4 is 1300 Kelvin. This is what T4 is. We still need to find P4, but again, we have a relationship for that. We have the isentropic relation, T4 over T3 equals P4 over P3 to the power of gamma minus 1 over gamma. We just found T4. T3 we found already over here. P4 is what we're going to try to find the same way we tried to find P2. Mathematically, these are exactly the same steps. And P3 we already found over here. Gamma minus 1 over gamma. So again, 1.4 minus 1 over 1.4. That's the exponent. Now, if we do this, we're going to find P4 is 480 kilopascals. So if we just isolate for P4 the same way we did here, over here, we're going to get P4 equals 480 kilopascals. So at this point, we've solved for the temperature and pressure at every point, which is what was asked of us. But they also ask us something else. And the something else they ask us is to find the thermal efficiency. Now, thermal efficiency refers to how efficiently you're turning your input heat into useful work, okay? Because we know in any cycle, we're going to have to reject some heat in order to come back to the initial state. That's a given, right? But we don't like rejecting heat because it's kind of a waste, right? But we want to make sure that we're being as useful as we can be, in that if we put in 100 joules, we want to use up as much of that as we possibly can, right? Because everything we don't use is wasted as Q out. It's rejected later on. So thermal efficiency refers to how good we are at making use of Q in and turning it into work out. So put simply, the eta, which we refer to as efficiency, the Greek letter eta represents efficiency. Thermal is equal to the work output over the Q input. So if the work output is like 50 and we put in 100 joules of heat in the combustion process, well, then we have a 50% efficiency. But we also know from the first law of thermodynamics that all the energy in a system has to be accounted for. So if we have a Q in and a Q out and a work out, that means that Q in equals Q out plus work out, right? And that means that work out is equal to Q in minus Q out. So the thermal efficiency can also be expressed like this, which is 1 over Q out minus Q in. So we've just developed this way of expressing how good we are at turning heat into work. Now let's actually find out what that means in terms of this specific problem. So Q in was a given, right? It's this guy over here. This is our Q in. It's telling us that we're putting in 1,800 kilojoules per kilogram of heat into the system, right? Now, Q out is what happens between steps 4 and 1. It's what happens in the condenser. It's where we're rejecting heat. But the way we reject heat is the same way we added heat when we looked over at this guy, right? We're going to reject heat such that T3, sorry, not 3, or T1 minus T4 equals CV, sorry, excuse me, I messed up there. Remember, we're talking about the change in internal energy. So U1 minus U4, which is the change in internal energy across the heat rejection process, so the condenser we call it, equals CV T1 minus T4. We know T1, we know T4 because we've just solved for the entire system's state at every location. So if we find CV T1 minus T4, what we'll find is a negative number, which we expect because we're rejecting heat, we're losing heat. We got 782.3 kilojoules per kilogram. This is how much heat we're giving away just so that we can come back to the initial state and continue the cycle. So we're gonna calculate this in a second, but I just want to make sure it's clear what's going on. We have some heat added, and we're going to use that heat to produce work. But we can't use all of that heat to produce work. We have to reject some of it because by the end of the process, we do need to come back to where we started. Otherwise, it's not a cycle. So we have heat that we input, we have work that we get from that, and the leftover is rejected. So what you're seeing here is the leftover that we have to reject in order to come back and continue the cycle, all right? And of course, if we added 1,800 and we gave away 782, that means that the amount of work we did is 1,800 minus 782, and that gives us 1,017 kilojoules per kilogram. That's the amount of work that the system is doing every time we go through a cycle, right? That's the amount of work that the car engine, in this case, is producing, if you want to look at it like that. But again, they're asking for the efficiency, and we just came up with the little equation for that, which is Q out over Q in. So 782.3 over Q in. And of course, the efficiency always has to be less than 1, because otherwise what that means is you're producing more useful work than you put in heat, and that makes no sense because that's a violation of conservation of energy, right? So anyways, let's do the math here. 1 minus 782.3 over 1,800, and that gives us 56.5%. Well, it gives us 0.565. So 56.5% thermal efficiency. So what does that mean? That means that only 56.5% of the heat added into the system is actually being used as work. Everything else is being rejected, right? And this is sort of one of the main goals of thermodynamics for engineers in general is we want to see how we can increase the efficiency of these kinds of systems to minimize the amount of energy that we're wasting, because Q out is all completely wasted, right? So we have to find, creative ways of how to minimize Q out, maximize work out for a given Q in. And, in Thermo 2, you're going to see a lot of different techniques of different other devices we can add in the middle of the steps between the cycle, between the processes that help increase the efficiency. But what you want to understand from these kinds of examples are the very qualitative relationships between what parameters affect the efficiency. And later on, you'll see that, for example, the thermal efficiency in this cycle is defined almost completely by the compression ratio we saw over here. And we see that you will see that the bigger the compression ratio you have, the better the thermal efficiency. So if you're designing this kind of system, you want to try to make as much as you can. You want to try to make as much as you can a very high compression ratio, and that will increase your thermal efficiency, and it'll decrease the amount of heat that's wasted, and it'll increase the amount of power you get for a given heat input. So I know this was a really long example, but this is really the crux of thermodynamics 1. You're going to see a couple different types of cycles. This is just one. This is the Otto cycle. But it's really important that you understand the sort of philosophy behind how to solve these questions, which is you want to first draw out your cycle like we did, and you want to identify the types of processes that are occurring. Is it isentropic, isochoric, isobaric? Is it something else? You want to identify all these types of processes right from the get-go. And then you're going to use your knowledge of the state, maybe at state 1, combined with any combination of ideal gas law, property tables, knowing what type of process is what's held constant throughout that process. You're going to use all that information to find the states everywhere else. And then by knowing the states, you know things about the internal energy or the enthalpy, and you can use that to find the amount of work output, the amount of heat input, the amount of heat output, as in heat rejection. So this is sort of what you want to be able to do. So I know it's a long video. It's a lot involved, a lot going on here, but it's really important that you understand how this works. Watch it as many times as you need, do as many practice problems as you can, because it's really, really, this is what thermodynamics is for.